In this video, I'm going to explain shockwave and queuing theory. So, introduction to the models. Shockwave and queuing theory are theories that are important techniques to use for modeling freeway congestion. Both of the methods are used to estimate the queue lengths, travel time, and delay. Both estimate the same delay, but they have different definition of queue lengths, which will be explained in the later slides. Additionally, both techniques are deterministic, which means that flows are not at random, they're more set in continuum approximations that treat traffic as a compressible fluid rather than individual vehicles. Lastly, both are related to the fundamental relationship, which is Q equal VK. Q is flow, V is speed, and K is density. And xt here represents x's location and t is the time. And right here, it's important to note that density here is not the independent variable that causes increase in the flow. Flow is just constrained by the capacity of the roadway, and density is determined by the flow and the capacity constraints. So this graph represents the example of the density flow relationship. The horizontal axis here represents density, and vertical axis here represents flow. And the left curve here represents the uncongested traffic, and it has low density. And the right curve here has higher density and represents the congested condition. And slope of this curve here actually represents the velocity. So if you take a look at this equation here that I explained, you can actually retrieve the velocity by plugging the data point. So for example, if you actually choose one data point, let's say this one, it'll be 20 for density and 2000 for the flow. So let's plug in here, which will be 2000 equal 20 times V. So which will make V equal 100 kilometer per hour, and the equation would write it as Q equal 100 kilometer per hour times K. And also, if you take a look at this graph right here, this uncongested traffic, it stops at 2000, and the congested traffic actually stops even lower than that. So what this tells is that this graph is actually unfinished, and to find out where this congested and uncongested traffic meets, that's when we use shockwave or the input-output method. So this graph right here shows how shockwave and input-output method estimate travel time, delay, and queue length. So let's first take a look at this illustration right here. So let's say the vehicles at x0 right here is trying to reach their destination at x4. However, on the way to x4, they encounter congestion because the lane merge at x3. And if you take a look at this graph right here, this line represents the arrival flow, and this line represents mu, or the bottleneck capacity. So once there are more cars coming in than the bottleneck capacity, there is congestion created. And during this congestion, the mu is equal to discharging rate, because only the bottleneck capacity can be discharged from this area. And once the arrival flow falls below the mu, it means that queuing starts to diminish from this point. So let's take a look at this first graph here, represented by the shockwave method. So the horizontal axis is time, and the vertical axis is location. And it's first divided into 8 different regions, depends on the density and flow of the traffic at the time, location, and the time. So it assumes that the vehicles that left before beginning and at the end of the queue would not encounter any congestion and would reach their destination at free-flow travel time. So let's say vehicles that left at T0 would reach X4 here at T1 time. And this horizontal distance between T1 and T0 is represented by torque, which is the free flow travel time. And same thing applies to T12, which reaches at T13 here. And the other vehicles that left between the T0 and T12 here, they would actually encounter the congestion even before reaching X3. So this lighter dashed line here shows how the free flow travel would be if there was no congestion at T6. However, because there were congestion, the vehicles that left at T6 movement is more tilted down and actually arrive at this time. So the horizontal distance between the free flow arrival time and the congested arrival time, this represents delay, and then it's written as letter D. So this middle graph right here represents the input-output method. So the horizontal axis represents time, and the vertical axis here represents the cumulative vehicle count. So the top curve here represents the arrival vehicle count, and the bottom curve here represents the departure vehicle count. And these 2 points where these 2 curves meet represents the beginning and at the end of the queue. So this end of the queue is also called points of dissipation, and it is same thing as beginning of the queue here and the end of the queue here from the shockwave. So first, in order to calculate the queue length, which is in the vehicle count unit, you will get the longest distance between these 2 curves. So longest vertical distance. So let's say the vertical distance is longest right here. So you will get the vehicle count from this point from the arrival vehicle count, and this point from the departure vehicle count, and it will give you the longest queue length, which is in vehicle count unit. And in order to calculate the maximum time delay, you will get the longest horizontal length. So let's say the longest is right here at this point. So you will get the time from the departure and this time from the arrival vehicle count, and it will give you the maximum time delay. And lastly, in order to calculate the total time delay, which is in unit of vehicle hour, you will get the area between these 2 curves, and that will give you the total time delay. Now I'm going to talk about how input-output and shockwave theory differs. So it differs in the definition of the queue length. So this illustration right here is the input-output method's definition of queue length. So what it does is that it assumes that drivers that leaving X0 would reach X3 where the congestion is at the free flow rate. So it assumes that drivers would not encounter any congestion until going to the X3, and once it reaches there, it assumes that vehicle would go on this top of imaginary vertical stack and discharge from the bottom. So let's take a look back at the input-output graph here. So this, like I said, this top curve represents the arrival vehicle count, and this one is drew based on the density flow relationship, the uncongested density flow relationship. So right here, the slope of this curve is 100 km/h. So what it does is that this arrival curve assumes that the drivers would reach the point of X3 where the congestion is at the speed of 100 km/h. And then let's take a look back at the shockwave theory. What it does is that it actually rotates this imaginary vertical stack into to the horizontal axis, and it assumes that drivers would encounter these gray congestions even before reaching X3. So let's take a look at this graph here again. So the drivers leaving from the X0, they would encounter the congestion even before reaching X3 here. So these boundaries between these regions is called shockwave. That's why it's called shockwave theory. And the slope of this shockwave represents the velocity or the speed of the shockwave. So when it's negative here, it means the shockwave is increasing down here. And when it's positive, it means the queuing starts to decrease. And that'll be it. In this last slide, this is where the research article that I drew the information from. And if you like to take a look at it, there is the link right here that you can go to.